Okay, we can start. Domanda iniziale, a preliminary question. Are there colleagues or students who prefer the seminar in English? Sì, in English only two, all the other no. But, okay, anyway, I think that the Professor Carlo Barbante...
I can do that in English, is a pleasure, no worries.
Okay. Okay, so it is a great pleasure to have again Carlo Barbante as a speaker to our colloquia. His colloquium, President Colloquium was on 29 November 2012, 7 years ago, on the same topic, not on the same data, okay. Global climate change and the human impact. The exact title was Earth Climate, the lesson learned from the past. This is, of course, as I think all you know, a particularly topical issue today after the conclusion, an inconclusive closure, of the conference COP25 held in Madrid a few days ago from 2 to 13 December. Carlo Barbante is the director of the Institute of Dynamics of Environmental Processes of the Italian National Research Council, CNR, and full professor of analytical chemistry at the Department of Environmental Science, Informatics and Statistics of the University Foscari of Venice. He is mostly known for his contribution to the fields of paleoclimatology, past biogeochemical cycles, and analytical methods development. Specifically, this contribution included the reconstruction of past atmospheric pollution through polar and alpine ice core analysis, as well as the development and use of novel analytical approach based on inorganic, organic mass spectrometry. In all of this field, he has played a substantial role in the production and understanding of data sets that have revolutionized our knowledge of the history of the Earth system. He has been awarded a grant from the European Research Council, ERC Senior Grant, and his project with the title Early Human Impact dealt with the reconstruction of the impact of human activities on climate. He serves as the Italian national representative to Horizon 2020 for the societal challenge, climate action, environment, raw material, and resource efficiency. So, I now give the floor to Professor Carlo Barbante.
Thank you very much. So, listen first, and then you clap me eventually. No, I was looking at my presentation of 7 years ago, and indeed it was mostly devoted to my year C, the work I did on the year C, reconstructing fires in the past, and it was a great adventure. We did develop first new method for the analysis of the ice and marine sediments and lake sediments, with a new method for proxies of fires. Then we reconstructed the fire distribution all over the world in many different archives. But today I want to tell you, I want to speak about the future in terms of what will be our climate tomorrow, and how we know that it will be like that, and what are the knowledge gap that we have, and we want to fill the void in the near future, because there are a few projects, and especially one that I'm going to speak to you, that is really worth mentioning about that. So we are dealing about climate. Everything on our planet is connected through the atmosphere. You know that this planet is unique, certainly in the solar system, and most likely, in a pretty wide part of the universe. Anyway, is more than 6,300 kilometers of radius, but just a very short, tiny atmosphere. And within this atmosphere, all the processes and the exchange of energy and many chemical reaction happens. You know that our troposphere, which is just 10 kilometers thick, has a variety of gases inside. Of course, nitrogen and oxygen makes the major role, but the greenhouse gases are extremely important because they keep our planet warm enough and sustain life on the planet. There are a few things that I want to show you to set the scene, and it is these three very last report from IPCC. IPCC stands for Intergovernmental Panel on Climate Change. The first one is on the 1.5 degree. I will refer to it many times. We recently translated in the frame of the National Climate Science Society. There is this one that appeared a few months ago on climate change and land, and more recently, the very, very important the SROC, the ocean and cryosphere in a changing climate. Ocean and cryosphere are certainly the most vulnerable part of our climatic system. And since we are in a department of physics, I want to take the opportunity to speak about this. This is a book, it's a collection of articles that make the fundamentals of climate sciences. When we are speaking about global warming, we are speaking something that is known since the 1850s. When Fourier, I mean that everybody knows, started to study the interaction of the lights and materia, and trying to make the balance of the energy balance of our planet and other planets. And then at the middle of the 19th century, Tyndall demonstrated that when you have molecules like CO2 or methane or N2O in the atmosphere, they interfere with lights, they absorb energy, and then increase the temperature. But it was just in the end of the 19th century, 1880, that Arrhenius, that everybody knows, formulated the greenhouse gas hypothesis and said greenhouse gas is, CO2 is one of the most important greenhouse gas, keeping an important role in warming the planet. And he also postulated and said if the CO2 concentration in the atmosphere, it was 1880, that at that time was about 300 parts per million. If this concentration will double, the temperature of the Earth will increase of about 6 degrees, which is not that far from what we know today. Best climatic models says us that the temperature increase, and now we take into account all the feedback effect, all the radiative forcing, will be of about 6 degrees if we double from 300 to 600 the concentration of greenhouse gases. So it's something that we know since a long time. And even more recently, in 1911, Giacomo Chamichan, who was an Armenian chemist born in Trieste, he worked for a quite long time in Bologna, and the Department of Chemistry in Bologna is entitled after Giacomo Chamichan, published a paper in Nature in 1911, and he said, if we continue to burn coal at this rate, I mean, we will increase the CO2 in the atmosphere, and this will have a strong effect and a strong impact on climate. So it's something, the same old story, as I would say from a scientific point of view. But things are really changing in our planet. This is a history of the temperature of our planet reconstructed from marine sediments over the last 2.5 million years. Okay, that is a proxy. Delta O18 is not exactly the temperature, but is a proxy that we use to mimic the temperature of the planet. And you see that there are changes in the temperature, fluctuation. You see a general cooling trend of the planet over the last 2.5 million years. Why 2.5 million years? Is because at that time, our continents were already in the position where they are today. Oceans were occupying more or less the same position. So the Earth was already working in the way in which we know today. So these fluctuations are well known, are glacial cycles. You see cold period and warm period, cold period and warm period. With with the differences, of course. If you look at that and if you apply a power spectrum to this data set, you will see that for a good part of the spectrum, this goes with a 41 kilo-year periodicity, while in the most recent years, and we are living in this period, I mean, the periodicity is of about 100 kilo-years. So there are things changing, and we don't know exactly the reason why climate is changing from this periodicity and this one. And this will give me the chance to speak about that. This is a zoom on the last part of the curve over the last 150,000 years. This is instead is a Greenland ice core. So that's a marine sediment, that's a Greenland ice core, where you see exactly the last the Eemian, so the previous interglacial, which is quite similar to ours, although our is lasting for much longer. And then you see periodicity, which we can refer very easily to orbital parameters, and I will come to that in a minute. This is again different records from Western US marine sediment record. This is again an ice core from Greenland where you can reconstruct the last 50,000 years with a very, very high detail. So what you can notice here is the stability of the last 10,000 years. The climate of our planet over the last 10,000 years, this period is called Holocene, is incredibly stable. We never had something like that over the last previous 2.5 million years. It's extremely stable. And you notice that during the glacial, I mean, over the last 50,000 years, the climate was a bit bumpy. And when I say that, I mean that from one point to this, from this point to this one, there are about 10 degrees in temperature. So those are fluctuations that we call abrupt climate changes. So we had rapid climate changes, but only in glacial period of time. We never had something like that inside here. And we are doing our best to have a new abrupt climate change in the near future. Because what we are doing is that we are really forcing our system out of the equilibrium. So basically those fluctuations that you have seen on the periodicity of 41, 23, and 100 kiloyears are tightly linked to the insolation over the different period of the time because of the orbital parameters. Actually, there are three main orbital parameters that influence the amount of solar radiation that arrive at a certain date at a certain point. The obliquity of the terrestrial axis, the precession of the orbit, and the eccentricity of the orbit. The last one, which has a periodicity of 100 kiloyear, however, has only the effect of modulating the other two. So the big fluctuation that we see over the last few 100,000 years are not tightly linked to the eccentricity, but is something which is internal to the climate system. So when I spoke about abrupt changes, I also want to put them in the context of what is happening today. Those are the temperature over the last century, a little bit more, from 1880, both land temperature and the ocean. Ocean respond in a slower way because, of course, the thermal inertia of the ocean. But overall, I mean, when you consider the average increase of the temperature, you see that the average increase over the last century is about 1 degree in average, which is a lot from a climatic point of view. Something which is also important is that this is an average temperature. So we have a quite fast increase, especially the increase of the last few decades is really worrying and fast. But what happened from a global perspective, I mean, the temperature is not equally distributed all around the world. And if you look at the 1880-2017 period of, in average of about 1 degree, you'll see that it's not equally distributed. There are places in the world which are warming faster than others, places which are really cooling. You see the time going on here, 25, 30, and so on. There are other places which are really warming very, very quickly. And especially, there are a few areas in the north, in the Arctic, and now in the most recent years, also in the Antarctic Peninsula, just on the continuation of the Andes, I mean, where the temperature are increasing really in a really fast way. And especially in the Arctic, where we have about 3 degrees in terms of 3 degrees in terms of increase in temperature, is something which is really unprecedented over the history of our planet. And there are explanations for that. There is a phenomenon, a process called Arctic amplification that is based on mostly on feedback effect and on amplification processes that happen in the Arctic and also in some part of the Antarctica. And this has a lot of consequences. If you want to point out what is happening in Italy, Italy is also an hotspot for climate change. Again, there are areas of the peninsula which are warming faster than others, and especially the Alpine region is certainly one of the most critical from this point of view, where the differences in temperature are higher than the rest of the peninsula. So this is the reason why we are worrying about. I told you already that we know the physics behind that, we know the chemistry behind that, we know that the huge increase and the gigantic increase in the CO2 that we had over the last century is the responsible for that. The human influence on the climate system is now clear. I mean, the degree of knowledge we have is very, very high. And this has a lot of impact, especially in the atmosphere, in the land, in ocean. Extreme events doesn't mean just rain, but it means rains sometimes. It means very, very hot on other circumstances. The danger in the future will be more coming from the heat waves than probably from the drought that we will have. And then again, ocean and water cycle are highly perturbed by that. Sea ice, which is literally disappearing very, very quickly especially from the Arctic. Glaciers, which are melting. For those of you who are used to hiking the Alps, you can see really the glaciers, which are considered literally sentinels of what is happening. And the ice sheet in Greenland and Antarctica are literally under threat. Of course, with a great impact, especially on the last few, on a mean global sea level rise. That's something very, very important. But if we want to put that in a context, I mean, we should look at natural changes, and a fantastic record for that. We can get it from ice, especially from high elevation sites in the Alps, around the world, or in Antarctica and Greenland. Ice, as it falls down, include inside dust and particles, but also in the transformation from snow to ice, it brings together and it brings inside the bubble of the air. So you can have air inside and you can have the snow and the ice outside. So we go in these sites and we retrieve these cylinders of ice, very long cylinders of ice, which store a lot of information. As I told you, we don't see nothing here? Okay, you see that on the back, sorry. I mean, this is a piece of ice, and those bubble, tiny circle that you see are just bubble of air which are entrapped into the ice. This is less than 1 millimeter, something like this. And ice is a very specific, a very peculiar proxy, a very peculiar archive, because it holds inside the same record both forcing factors, greenhouse gases, which are entrapped, dust, and other mineral, and the response, because we can measure the temperature of the past looking, for instance, at the stable isotope composition of the ice itself. So, and this is the reason why, and this is the way in which we did measure the, for instance, methane concentration in the bubble, the CO2 concentration in the bubble, and we refer to the temperature of Antarctica over the last 800,000 of years. So this was a gigantic effort to retrieve this ice core. It was more than 3 kilometers long. The project is called EPICA, European Project for Ice Coring in Antarctica. It's start to be more than 10 years old project, but still an iconic graph refer to that. Where you can see the cycle that we have seen before. We are living more or less somewhere here with the last glacial, the Eemian, the previous glacial, and so on and so forth. And you notice something, I mean, that while minimum temperature have always more or less been the same, the maximum are going to be warmer and warmer and warmer. And there is a difference because, again, we are looking at something which is on the 100 kilo-year cycle with a fluctuation, very ample fluctuation, but with a higher periodicity, with a low periodicity, higher periodicity and low amplitude in the previous part. This is an unknown. I mean, we still don't know what is going on here, and until we will not know that, we will not have a clear clue on what is happening also today, because the sensitivity of the climate to greenhouse gases has to go through processes like the carbon cycle and so on. So again, if you look at that and if you put things together, this is again the record over the last 800,000 years, with the CO2 record, we change in the same phase with the temperature over the last 800,000 years. As I will tell you later, I mean, we have no other record that allow us to go back in time, far back in time of the 800,000 years in the ice. And ice, as I told you, is very important because I say it again, on the same record, we have both the forcing factor and the response of the climate. And today we are here. So this is the fluctuation we had over the last 800,000 years. And today we are consistently over the 410 parts per million. So our climatic system never had such a concentration. We have to go back at least 5 million years if we want to find another point in our Earth history where the climate was at such higher concentration. So that's an incredible amount of time. So, and looking at the understanding what's going on and putting things together and detecting first and attributing that to the greenhouse gases, this is again the observation that we have seen. I mean, it's a very rough observation. We can know the physics behind that. We know the chemistry and the processes happening. We can model all that. And so bringing all the things together, of course, we don't have an equation of the climate. It's pieces of things that are taken together and that give us allow us to reconstruct the temperature. But if we put all together and we model what was the temperature over the last 120 years, and we compare with the observation, and we take into account all the forcing, which are natural plus anthropogenic forcing, we have something like that. And so, again, what we can do, we can try to remodel our climate considering just the natural forcing that we know quite well. We know the dust, we know the particles, we know the greenhouse gases in the atmosphere, and so on and so forth. We know the solar radiation, we know the effect of volcanoes on cooling climate, and so on. So if we go and model that over the last century without considering anthropogenic forcing, this is the curve that we obtain. So with anthropogenic forcing, without anthropogenic forcing. So there is a huge difference, and this is what is clearly due to the human impact. So the observed changes that we have are consistent with the expecting responses to all forces and are really not explicable with alternative explanation. Consider volcanic forcing or solar forcing. But again, something which is extremely important, again, in terms of impact, are the polar region, both on the Arctic and in Antarctica. Those are certainly vulnerable places. They are under threat because of global warming. I told you Arctic is suffering of the Arctic amplification plus 3 degrees in average temperature in the Arctic, while the average temperature all over globally is of about 1 degree. So plus 2 degrees, which is a big thing. And the impact on that is on sea ice, for instance. If you look at the sea ice volume over the last few tenth of years, I mean, is incredibly low. I mean, we lost 60% of the ice in just few decades. And what is lost is not just the surface, but is also the thickness of the ice. So the volume is incredibly low. So we are losing thickness and surface of the ice in the Arctic. That will open, of course, the discussion. I mean, because when you have a shrinking of the ice, you have more water exposed, and the water absorb energy. The ice is reflecting the energy, so this phenomenon is even more accentuated. While we don't have any direct impact of the sea ice on the sea level rise, because the ice is already in equilibrium, it has an indirect effect, but I don't want to discuss it. While the sea ice have no direct effect on the sea level rise, when you consider huge continent like huge ice sheet like Greenland or Antarctica, and you see the ice loss that we have over the last few decades, I mean, we lost hundreds of gigaton per year of the ice. Greenland is melting from above, Greenland is melting from below. I mean, either on the ice sheet, on the ice shelves floating into the ocean, either on the interface in between the ice and the bedrock. Is about 280 gigaton of ice per year, which has a contribution on sea level of about 0.8 millimeter per year, which is quite a lot. Same story for Antarctica. Antarctica wasn't a steady state until 15 years ago. Most of the Antarctica was in a steady state, no real loss of ice, no real increasing of the size of the ice sheet. But what is happening in the last few decades, I would say at the starting of the 2000s, is really remarkable. The amount of ice lost, especially from this part of Antarctica, the western Antarctica, from a few glaciers, Totten Glacier and a few others, this, to give you an idea, as a potential contribution on sea level rise altogether of about 7 meters. So is under control, very strict control. Is of about, again, if we consider that, is about 125 gigaton of ice per year, which is about 0.35 centimeters, which is a lot. I mean, if you put together all the things, if you put together the expansion of the ocean because of the warming, we'll see that it makes a huge difference. And on top of it, you have to put all the non-polar glaciers, which are really under threat. They are really the first that will completely disappear. There are models that are projecting into the future, and over the end of the century, all the glaciers of the Alps below 3,600 meters will be completely lost. And as said, I mean, the contribution of total glaciers, non-polar glacier, to sea level rise is not that much. It's just 30 centimeters, something like that. If you melt all the glaciers, not polar glacier, you have a contribution to the sea ice increase like that. But they are there, I mean. They are melting right now. So that is the first things that will melt is non-polar glaciers. And something which is happening in reality, this is Greenland, is something like this. You have rivers, long rivers and lakes of water on the surface of Greenland that are melting during summer months. They run for kilometers until they found crevasses, and then they goes down at the very bottom at the interface in between the ice and the bedrock. And that's something which is more and more and more frequent, and we never had it in the past, or very, very seldomly. Because when we dig an ice core in places like this, we can see if we have ice lenses and if we have melting, if we had melting on the past. And it's something which is very, very seldom. And as I told you, this melting, the melting of the Greenland ice, the melting of mountain glaciers, the melting of Antarctica has a direct impact on sea level rise. This is the last few decades of sea level rise. If you consider that from the 1880 to 2000, sea level rise was about less than 2 millimeters per year. Now, from 2000 to 2015, is less than 3.6 millimeters per year, and in the most recent years, is nearly 5 millimeters per year. So the speed in which the ice is melting and the sea level is rising is increasing and increasing in a really worrying way. Again, glaciers, non-polar glacier, Greenland and Antarctica are losing mass pretty quickly and strongly contributing to current and future sea level rise. So, where are we going? I mean, what is happening to our planet? Really, I mean, this is again a curve which has been published a few years ago from Marcotte in Science, which show you the reconstruction is a stack of data putting all together from many different sources, not just ice core, but including tree rings, for instance, lake sediments, to have the best reconstruction of the temperature over the last 10,000 years. On the left, there is the last ice age. Our period, I mean, started here, so we have what we call the Holocene optimum. You'll see the differences in temperature is already, from the pre-industrial value to today, is already 1 degree. And if you put in the scale, I mean, this is really an abrupt climate change. It's what we have seen before in the long record happening during glacial. We never had something like that in an interglacial. But speaking about Paris, we are not that far. I mean, the trajectory in which we put our planet from a climatic point of view is here. And again, if we want to look at what will be the future, that is the business as usual scenario. You know that climatologists produce scenario to see what will happen in the future, and scenarios mostly based on greenhouse gases emission. We know the relationship. We know quite well how greenhouse gases is translated into temperature, and so we can build up future scenarios. That's really an abrupt climate change. It's typically what happened during a glacial period of time. In a few tenths of years, several degrees of temperature. And this is something which really can change the life of a planet. So, and those are the projections, as I told you, regarding the temperature or the sea ice, again. Projections are, again, the 8.5 scenarios, or so the business as usual scenario, or the best scenario. I mean, trying to keep the system under control, keeping the equilibrium of the system, and you see that reflected into the sea ice. Again, in the worst scenario, by the middle of this century or a little bit longer, there will be no longer sea ice in the Arctic at the end of the summer. There was a paper you probably see in the press as well, dealing with Marmolada glaciers, which is just next door. In 30 years from now, it will be completely disappear. And I tell you a story, the mountain glaciers are really, and the alpine glacier in particular, are really vulnerable, because whatever scenario you have, either if you can keep the climate at the very, very low CO2 emission scenario, I mean, for the next 30 years, nothing changed for the glaciers. They are gone everywhere anyway. I mean, the reaction of the glaciers to the temperature, to the flow that they have, of course, depends on the slope and so on. But anyway, for the next 30 years, regardless by the scenario that you have, even if it is a very conservative or it is a business as usual one, they will get lost anyway. Something will change after 2050. If you keep a very scenario like this one, with a zero emission, carbon-free planet for 2050, then the things might change for the second half of the century. Again, we are tied to the emission, as I told you. This is again the emission over the last 140 years, more or less, since Rio 92, where people realized that it was better to stop the emission grow up of about 2% every year. So since Rio 95, we have more than 60, Rio 92, we have more than 60% increase of annual CO2 emission. And this, as I told you, can be translated, can accumulate in the atmosphere and can be translated into temperature. And there is this interesting graph that put the cumulative anthropogenic emission together with the temperature. Again, this is our trajectory, I mean. So this is clearly something that we know where we are going. And again, since we know how much total anthropogenic CO2 we are injected into the atmosphere, we can see where is the threshold point for the 1.5 degree or to the 2 degree. And to answer the question of my title, is too late for 2 degree, is probably too late. If we continue like that, it's literally too late, because this is the warming trend. This is our future. At the current warming rate, we will probably arrive in around 2040 to the 1.5 degree, and later on to the 2 degree. But we have to improve our knowledge at that point. We have to improve our knowledge about the climate sensitivity. I told you Arrhenius work on climate sensitivity. What is the increase of the temperature if we double the CO2 concentration? That's climate sensitivity. And we don't know that much. And that's the reason why I go back to the ice again. This is the reason why we need to improve our knowledge on the processes that put together the changes in the temperature and the greenhouse gas concentration. We must know much, much better what is happening and how CO2 and methane are impacting on the temperature. Because our system, and as again you see changes from 800,000 years ago with a high frequency and low amplitude, and then higher amplitude and lower frequency. Something is changed over here. So, and even the sensitivity of the gas, of the climate to the greenhouse gas forcing has changed quite a month ago. It is very, very interesting from a physical point of view, the process that is happening. I mean, our system, this is the temperature, this is the sea level, has always fluctuated through a warm period, what we call the interglacial, to a cold period. So higher sea level, lower sea level, higher temperature, lower temperature. Of course, the system doesn't go back and forth on the same line. There is an hysteresis in the system, you know. But what is happening today, and I want to show it here, is a bit complex, but it gives you the idea. This is the line of time. This is stability, which is inversely proportional to the potential energy. It means lower potential energy here and higher, a very unstable system here. So over the last millions of years, Earth has always gone from cold period of time to interglacial, cold and warm, flipping from one state to the other one. Now we are living in a very stable period of time, which is called the Holocene. But since we enter in the most recent epoch, you know, the Anthropocene, where we are really impacting our system, things are changing. And we are really at a turning point right now. We are really at the point where either the system goes inside what is called the hothouse Earth, and is what is called the planetary threshold. We are now in a trajectory which is completely different from what we had until a century ago. Or either we can keep them and stabilize our equilibrium within a certain domain. So we are far now from the glacial interglacial cycles, what we had over the last few million years. We are now on a completely different trajectory of our climate. So we can either escape and go on literally an unknown system, I mean, where it is really difficult to predict, even because we don't know exactly how are these feedback effects behaving under a stress system, or we can stabilize the Earth and keep it within a certain point. And for that, we should improve our knowledge, again, on the sensitivity of our planet to greenhouse gas changes. So this is the atmospheric CO2 concentration. We are now more or less here, and this is the differences in temperature. As you see, it's not a linear system, so we should improve and, or better, fill the gap, trying to decrease the uncertainty that we have here. So we have to test how our planet worked in the past regarding, for instance, CO2 concentration and the greenhouse gas. Also because, as we have seen, I mean, the climate literally changed. Again, this is the history of our planet over the last 1.5 million years. This is a curve that resembles we have a proxy of the temperature. This is coming from marine sediments, but unfortunately on marine sediment we don't have the forcing of greenhouse gases. This is the ice core record that I've shown you already with the temperature and with the CO2, with the actual CO2 concentration, which is quite far of the previous 5 million years. We don't have everything. But something, I mean, which is really interesting for us is to look at the history of our climate here. How greenhouse gases and temperature change on this period of time, which is called the mid-Pleistocene transition. And it's a period of time in which climate moved from a very high frequency and low amplitude to a very high amplitude and low frequency. So from the world at 41,000 years to the world at 100,000 years. So if we know better what happened that, we can literally improve our knowledge. We can fill the void in understanding the history of our planet. So we have some data. I don't want to say that we don't have data, because there are data coming from marine sediments. You can use proxies like boron isotope to extract the CO2 concentration, very difficult task and very imprecise. You can use ice where you have bubble inside, but instead of being ice well stratified, is ice that is flown back again, so it's very old ice which emerged. We call it surface ice, which can be dated with absolute method in which we can have information. So the idea is to look at ice, a continuous ice down to 1.5 million years, which is not easy to find. And this is the part of the future that I want to tell you. That's a project that we are thinking about and we are aiming to and we are running right now. So we want to know what is the history of this mid-Pleistocene transition. So the transition from the 40-year kilo-year world to a 100-kilo-year world. We don't know why it happens, and unless we don't have a clue of that, we don't put in a better knowledge what is happening today. So there are several things that we are looking at. Of course, greenhouse gases, the temperature. We will look at the sea ice, ice sheet altitude, sea ice reconstruction, and many things that we can extract from ice core. So basically, if you know where to find ice, very old ice in our planet, please tell me. I mean, we are very happy to know. Although we have some clues, I mean, okay, consider that from this point to here is more than 5,000 kilometers, 14 million square kilometers of continent completely frozen, almost completely frozen. We have some clues where we can find very old ice, and this is along this line, which is the ice divide of East Antarctica. Again, there are places where we know there is very old ice, and this is blue ice, the ice that came from the flow back to the surface, and where the data that I've shown you are coming from. There are Anomalies and Grove Mountain over there, but most probably very old ice is here. So what is what kind of characteristic must have the ice to be very, very old? Of course, we need to drill a very deep ice core. When I say very deep, it means about 3,000 meters, which is not really very easy. We need to have very low accumulation because we want to go far back in time. It has to be cold. It has to be very cold and flat at the bedrock. Not too thick, because if it is too thick, you have melting, because the pressure melting point is coming up, and literally no flow. So to make a long story short, our candidate site is over here. Is nearby the Italian-French station, which is called Concordia. This is just an expansion. To go from here to here is about 40 kilometers. Most probably the ice that we found is over here, is in a place which is called Little Dome C. Average temperature is about minus 50 degrees. It goes down to minus 80, minus 89 during winter. It goes up at minus 35, terribly hot during summer. We don't like that because we want to keep the ice at minus 50, and this, from a logistic point of view, is a big problem. So we made about more than 20,000 kilometers of radar lines, so making scanning back and forth with radar echo sounding to find the right spot. And we found it. We have an ice core here. The record that I've shown you, the 800,000 years record, is coming from this spot. So we know the layering. So we run along this line, along this mountain range, radar echo sounding, and then a very, very highly defined grid. And we reproduce the layering of the radar. So we could keep the signal, the dated signal from the right down to the left is where we want to drill here. So we could keep isochrones and we could keep the data down from one side to the other one. And we know that this place, which is our candidate site, is very old. We can model more than 1.2 million years, hoping 1.5 million year ice. And especially is a continuous record down to the bedrock. So I want to show you a few more slides with the bedrock topography that you see. This is the surface. This is the isochrone, as I told you. So layers which have the same age, and we can follow from the old side to the new one. And this is the bedrock topography, which is not exactly flat. And so we had to be very, very precise where to go, because all around here, where you see the light blue here, and all around here is water. And we don't want to have water under ice, because water means mixing of layers, and so we lose the stratification. So actually, our candidate site is here. It's called Little Dome C, because Dome C is the main dome. We have about 2.7 kilometers of ice to drill. We just selected the sites a few days ago, literally a few days ago. We are preparing now the camp, and I want to show you. This one is funny because this guy hanging the EU flag is a researcher of the British Antarctic Survey. You know, we hope to have them still in the business. Okay, site has been selected. Most of you, I think, are physicists. I'm looking at the younger side of the audience now, PhD student or postdoc. Physics is a lot of things. I mean, is not astronomy. It's not just astronomy or particle physics or modeling. Is also environmental physics. We have a lot of physics working with us, and I translate and I make a sentence, you know, that Richard Feynman told that there is plenty of room in the bottom, not just referring to the small things, but I want to tell you that there is plenty of room also in open spaces like this. I mean, there's a lot of things we can do looking at the physics of the ice, looking at the modeling of the ice, looking at how the climate works, and so we need fresh minds for the future. I hope to have shown you something of interest for you. I hope to come back in 7 years from now, because I tell you, this project will last for the next 6 years. It's a it's like in the physics, you have big experiments, big science. That's big science applied to the climate. It's a 6-year project. We plan to reach the bedrock of the ice in 2024. Then to quickly analyze and to have another iconic record of greenhouse gases and temperature in the next 6 years. So I make a reservation for next colloquium in 7 years. Thank you very much.
inspiring and somewhat tragic colloquium. So hopefully in 7 years we hear better news. So I guess there will be a lot of questions. So please.
Thank you for your presentation, Carlo. Mine is more a curiosity about your opinion around geoengineering. Do you think it could be a possible solution to climate change, or do you think it's even worse than doing nothing?
It can be the question is about the geoengineering. Can we do something with geoengineering in the future, so carbon capture or whatever? I think yes, it's part of the business, but it's not a total solution. I mean, we have to find other ways, and certainly mitigation. So decreasing the emission of greenhouse gases is certainly the way. Increasing the efficiency on how we use our energy, produce and use our energy is another thing. All things have to go in parallel.
Well, can you comment about the document signed by leading
I was waiting
physicists?
for that question.
Yeah. Because, I mean, yes, please.
I mean, evidence is about warming is so clear and evident. And as I said at the beginning, we know that since a long time. There is a variety of opinion, but it's just a very few number of persons that thinks like that. You know, I mean, if you go on the literature, and if you think about that, goes on the literature, goes on Science, Nature, on other environmental and climate journal. I mean, there are virtually nothing about that can deny and support that. Absolutely.
Thank you very much for the talk. I have just a question. It's true that if the Antarctica has completely melted and exposing the ground, that will be an irreversible action. So whatever will be the action of the people for reducing the CO2, the reflection of the sun will be not enough from the melting by the ice,
yeah, sure.
and so will be irreversible the rise up of the temperature.
Nothing is irreversible. It means what is your time span? 30 million years ago, Antarctica was not glaciated. I mean, it was free of ice. Greenland, for instance, the glaciation in Greenland started when we started to have this very, very important. We went above that temperature threshold. So that means about 5 million years ago. So it's a cycle, but I mean, we are now living in this period of time, you know, and so we are really part of the system. We are really I would say, the most important forcing factor of our planet today.
Thank you for the talk. I have a question which might be naive. So you showed that there is a very strong correlation between the fluctuations of CO2 concentration and temperature from glaze analysis. So does this relation is also confirmed in the short time scale? I mean, CO2 has grown up dramatically, we know, but temperature has gone up by 1 degree, let's say. So is the same ratio between the rate of change of these two quantities or not?
Yes, it is. There are, I was saying before, discussing before my talk, there is not a linear relationship. There are several feedback effects, which I must be honest, we don't completely understand, that make things even, that will probably even go stronger in the future. So there is not a linear relationship, but there is a clear link in between the increase of CO2 and the temperature. Yes.
From those trends, you would expect the temperature to go much.
No, it will not go much faster than that. I mean, because there are, as I say, the feedback effects that they are positive, but they can also be negative feedback effects. So decreasing the initial input.
Just a technical question. If you put back the slide with the three curves on ice analysis, CO2 concentration, methane concentration, and temperature. As far as I understand, the temperature is a completely independent measurement. How do you do this measurement of temperature, not of gas concentration?
Okay, gases are done inside the bubble. You have to extract the air from the bubble. The temperature, again, is derived by the deuterium and oxygen analysis of the water. So we analyze the delta O18 and delta deuterium. So with the mass spectrometer, we do analyze the isotopic ratio of hydrogen or oxygen. And they are tightly linked to the temperature. Because when you have an ocean, evaporation and condensation depends on the temperature. And of course, when you have a molecule of water, which is made of oxygen, deuterium, hydrogen, it tends to evaporate less fast than a hydrogen, oxygen, hydrogen. So it's a very subtle and very elegant way in which we can measure the temperature, or we can go back to the temperature. Of course, there is a calibration. So for the calibration, we do use today's precipitation, where we measure the temperature of the precipitation, and we do measure the isotopic composition. It's very precise.
As precise as you should be.
Yeah.
Yeah, thank you for the talk. I have a question exactly about this this plot. So it's quite apparent that the rise time seems to be always a lot faster than the decay time. Every time there's a spike. Is that mechanism well understood? And
it's pretty well understood. And again, it's part of the feedback effect. Usually, we have a very fast transition from a glacial into an interglacial, and then the glacial takes more or less 100,000 years to go down to the minimum. You see, it goes quick and then deep down, quick and then down, quick and then down. Yes, this is quite well known. I mean, it's due to the feedback effect internal of the climate system.
Okay, since we are just looking at this plot, if I remember, if one looks in the details, in this plot, temperature starts rising before the CO2.
That's the chicken and egg question. Thank you.
Yeah, I mean, is there an explanation for that?
No, best data we have, because I forget to tell you something. I mean, the gas which is inside has not the same age than the ice. And the reason for that is that when the snow fall down, it pile up year after year. But of course, for the first, depends where you are, but for the first 100 meters, there are still open channels. So the air can diffuse inside what we call firn, which is very high densified snow. And if fall down, it diffuse, I mean, depends on the mass of the molecule. It diffuses down until a certain point where you have the sealing off, the close-off point. So when you have the close-off point, you're trapped inside ice, which is colder than the air inside. We know the difference in between the age of the gas and the age of the ice, because we know quite well the diffusion law that brings the molecule down into the bubble of air. So we know quite well. So if you make this adjustment, the changes in the chicken and egg question is, as far as we know for the dating, they go straight together. I mean, it's probably driven by the temperature, because it's a change in the solar radiation in the end. So I mean, the temperature comes first, and the gas follow immediately. But it can be also vice versa we are experiencing today.
And just based on your, of course, opinion, of course, it will be a wild speculation. In 7 years, the temperature, the increase in temperature, you expect to be?
Oh, I mean, it's hard to say.
It's very difficult to say. But based on the current
we will be probably
economical
near. I mean, on the way to 1.5 degrees. I mean, by the higher than it is today, but we might have. Of course, we have internal fluctuation of the climate system, internal variability that is due to El Niño events, to ocean circulation that can in some way cool or warm the system, you know. So it's not, again, a linear curve, you know. You can't extrapolate on that. But I mean, the temperature is steadily increasing, and it strongly depends on our commitments to reduce emissions in the future.
Other questions? If not, let's thank Carlo again. Thank you very much.
Thank you.